Hello everyone, welcome you all to this online NPTEL discussion class. I am Madhuri Bhattacharya, a Prime Minister Research Fellow in Department of Chemistry, IIT Madras. So we are discussing here regarding some important inorganic materials, their production, purification and utilization on industrial scale. So this course has been taught by Professor Debashish Rai from Department of Chemistry, IIT Kharagpur. So these are my details. You can contact me for your queries and clarification over my email IDs. So far we have discussed regarding some nitrogen phosphorus compounds, sulfur compounds also. So we have covered this one. Nitrogen, sulfur, phosphorus compound, halogen compound, some fertilizer, nitrogen based, then phosphorus based, potassium containing fertilizer, mixed fertilizer containing more than one elements, then some alkaline earth metal, alkali and alkaline earth materials like potassium mainly, sodium also. So today we will discuss some more alkaline regarding some more alkaline earth materials. Today we will discuss these things: beryllium, magnesium, calcium, strontium. These are alkaline earth materials, manganese compounds and their applications. These things we'll try to cover. Okay, and then some organosilicon compounds also. So the first question is, okay, the first question is about carborundum. Carborundum is a mineral actually. This is another name of which oxide? Silicon oxide, calcium carbide or silicon carbide. So this is actually not an oxide. This is metal carbide and the metal here is silicon carbide. So carborundum, trademark for silicon carbide, is an inorganic compound discovered by E.G. Acheson, and he has received a patent on it in 1893, and it has a crystal structure like diamond. It is very hard mineral. It is used as an abrasive for cutting, grinding, polishing. Abrasive means some scrubbing agent, okay, and anti-slip additive, and also as a refractory. So carborundum mineral is actually made up of silicon carbide, SiC, okay, silicon carbide. Silicon carbide, this one. Silicon carbide means silicon carbide, this one. So the polymeric structure of silicon carbide constitutes our carborundum mineral. Okay, move to the next question. Calcium carbide on hydrolysis yields methane, ethane and ethene. So the actual answer will be ethine or acetylene, because calcium carbide, as we can see from this reaction, CaC2, solid calcium carbide, upon hydrolysis it will yield to C2H2 known as acetylene or ethine and calcium hydroxide. Okay. Then what is the chemical composition of barite? So barite is none other than barium sulfate only. And barite is in massive crystalline structure or forms, and their basic chemical composition is actually barium sulfate. Okay. Then lithophone, a white pigment, consists of, the answer will be zinc sulfide and barium sulfate. It is a mixture of inorganic compounds widely used as a white pigment powder, and it is composed of zinc sulfide and barium sulfate. Reduction of chromium oxide by heating it with aluminium is known as smelting, roasting, calcination, or aluminothermite process. So the correct answer will be aluminothermite process, because it is the process for certain oxides like manganese, then your chromium, that do not reduce by carbon due to very high melting point. So for these oxides, they can be reduced by aluminium, and the reaction is as follows: chromium oxide plus 2Al leading to chromium 2 chromium plus aluminum oxide plus heat. Then an ore of manganese among the following is bauxite, hematite, pyrolusite, or cuprite. So bauxite is actually ore of aluminium, hematite is a ore of iron, then pyrolusite will be ore of manganese, and cuprite is the ore of copper. Okay. So the correct option is pyrolusite is a mineral consisting essentially manganese dioxide, MnO2 or Mn4 oxide. It is very important as an ore of manganese, and it is a black amorphous appearing mineral, often with a granular, fibrous or columnar structure, sometimes forming a rainiform crusts. Okay. The most abundant form of silicon is silicate, silica, silicide, or silicon carbide. So silicate means what? Silicon oxide actually. So silicate are none other than SiO4 4 minus, and then SiO3 2 minus, SiO3 3 minus, etc. Okay. Silica is SiO2. Silicides are actually the compounds made with some elements along with silicon, the elements which will be more electropositive than silicon. So here actually silicon present as silicon negative. Those are called silicides. For example, chromium silicide, then manganese silicide are also known. After that, CO5 Si, Mn3 Si, Mg2. Several silicide are known. Calcium 2. These are. Then silicon carbide means SiC. So the most abundant form of silicon is actually silica. Silica will be the correct option. B. Silicon dioxide or silica is the most common compound, is the most abundant compound in the earth's crust. It is commonly the form of ordinary sand, but also exists as quartz, rock crystal, amethyst, agate, flint, jasper, and opal. Silicon dioxide is extensively used in the manufacture of glass and bricks. Okay. Then what is the basic structure unit of a silicate? Silicates are made up with SiO4 4 minus actually. This is the building block. So SiO4 4 minus. Silicates are the metal derivatives of silicic acid. H2SiO3 can be obtained by fusing metal oxides or metal carbonates with sand. Sand is actually your silicon dioxide, right? So SiO2 plus your metal oxide like zirconium. For example, here zircon. Zircon is SiO4. So like zirconium silicon oxide, you can say. So it is made with zirconium oxide and silicon dioxide, ZrO2 and SiO2. If you mix together and fuse it, then zircon or zirconium silicon oxide will be formed. The basic structural unit here is silicon tetroxide, SiO4 4 minus. Then a p-type semiconductor results when pentavalent impurity is added to an intrinsic semiconductor, or a trivalent impurity is added to an intrinsic semiconductor, or either a pentavalent or trivalent impurity is added to an intrinsic semiconductor, none of the above. So p-type semiconductor means actually trivalent impurity is added. So here we can discuss a little bit regarding semiconductors. So first of all, conductors means there are actually three types of conductor material, right? Substances, conducting materials, or we can say substances, can be divided into three categories. Number one is conductors. Conductors means some band will be there in case of metals. Because why band? These are actually energy band. So this is called valence band, VB. This is conduction band, CB. This is like a band, not a discrete energy level, because several metal atoms will be present in in a sample of metal, right? Not only one atom we can imagine. We cannot isolate one atom. So several metal atoms will be there, and it will have several free electron, and those free electrons will have more or less same energy, leading to some energy band, not a discrete energy level it will have. So that's why band is applicable for any metallic substances. Then valence band, there are two types of bands, so CB and VB, valence band and conductance band, and the energy gap between these two is denoted as Eg. For conductors, this value, this energy gap actually determines its conductance property. For conductors, Eg will be 0 to 1 electron volt. Examples are alkali and alkaline, earth minerals. Alkali and alkaline earth materials. Okay. Then there is semiconductor. For semiconductors, Eg will be 1 to 3 electron volt. Example, group 14 elements like silicon, germanium, etc. Then, sorry, three. Third one is insulator. For insulator, Eg will be very high, greater than 5 electron volt. Example is diamond. Okay. For diamond, the Eg value is actually 5.5 electron volt. It should be actually greater than 3. For diamond, it is 5.5 electron volt. Now the semiconductors are divided into two categories. One is intrinsic. And one is extrinsic. Okay, so intrinsic conductors are semiconductors in the pure form. So there is no additive. So those are pure form, and yeah, here energy gap is like reasonable for having some conductance. So those are actually pure germanium, then your silicon, etc. And then for extrinsic semiconductors, these are like to enhance the conductance, we will add some additives. So some external intrinsic, like we can denote here, also intrinsic plus additives. Okay. So then like they are called actually doping. This process of adding additives to enhance the conductance is called doping. Okay, so there are, so the conductance of extrinsic semiconductors is greater than intrinsic. Right. And also for metallic, like for metallic Conductors conductance will be increased. Conductance will be not increased, will be decreased by increasing temperature. Okay, as temperature increases, conductance will be decreased due to increase of resistance, right? Since resistance is increasing. But for semiconductors, conductance will be increased as temperature is increasing, since Eg, energy gap, will be decreased, because actually more, this is not like energy gap will be decreased, rather we can say kinetic energy will be increased. Okay, kinetic energy of the conducting electrons from this valence bond to conductance bond, it will be, number of electrons will be increased. This is due to kinetic energy. Will be increased. So more number of electrons, number of electron in conductance band will be more. That's why with increasing temperature, conductance will be increased for semiconductors. So these are like the basics of materials: conductor, semiconductors, insulator, and then semiconductors are classified to two categories: intrinsic and extrinsic. Intrinsic means pure form of the metal, but when we add some dope, we add some additives like doping we are doing, then the conductance will be enhanced, and that is called extrinsic semiconductors. And conductance value for conductors will be decreased as temperature increases due to increase of resistance, but for semiconductors, conductance will increase with increase of temperature due to increase in the kinetic energy, supports the electron traveling from valence bond to conductance band. Now this extrinsic doping, extrinsic semiconductor doping, so extrinsic semiconductor can be two type. Number one is N type. And number two is P type. How does it look? N-type and P-type. N-type semiconductors are actually with group 15 elements. Like phosphorus, arsenic, etc. we will dope. And here it is group 13 elements. Like boron, aluminium, etc. Okay. So how does it look? This is the conduction band. This is the valence band. Since this is having higher electron density, so one more band will be there. This is the additives, donor impurity level. Okay, this is called CB. This is BB, and this is donor impurity level. Now this is having lots of electron because group 15, right? We know this is pentavalent, so 5 electron valency it has, and we are using group 14 intrinsic semiconductors where we are using the dopants, so it will have 4 valence electron. Then when some group 15 element is going inside group 14 elements belt, then 1 electron will be excess for each group 15 element, right? So that excess electrons band is this one, and these are the group 14 intrinsic semiconductors, valence band level and conductance band level. So the ionization energy, this gap, this is called energy gap, correspond to ionization energy. So this being smaller than this gap, that is the energy gap in the semiconductors, right? So IE is smaller than EG, right? So electrons will more easily go from donor impurity level to conductor's impurity and conductor's band than this one, right? Valence band. Here also electrons are there, then this one. So there will be excess of electron in CB will be more than holes in BB. Therefore electron is the majority carrier. Electrons is the majority carrier of electricity. And such type of semiconductors are called as N-type. N-type semiconductors means some negative charge is the majority character, right? Then for group 13 dopants, this will look like this one. CB, BB, and it will have one vacant site per each group 13 element, because this is having 3 electron valency. So each group 13 element will be bonded with 4 carbon, and not 4, actually 3 group 14 elements, and one site will be vacant. So that vacant site can be served as the whole positive. There is one vacant site. This is the acceptor impurity level. Acceptor level. Now here is electron. So IE, here also IE is smaller than this full IgY. So electrons from valence band will easily go to acceptor impurity level than this conductance band. So IE smaller than AG. So there will be more holes in VB will be more than electron in CB. So holes majority character are the majority charge carrier. Such type of semiconductors will be called as positive type of semiconductors, or like positive charge is the positive charge particles are the main conductors here. So this is called positive type, p type extrinsic semiconductors. So that's all regarding semiconductors. Okay, so that is written here. Actually semiconductors like germanium, silicon doped with any kind of trivalent atoms like boron, indium, gallium are called our p-type semiconductors. Okay, the impurity atom is surrounded by 4 silicon atoms only, but it provides the atoms to fill only 3 covalent bonds, as it has only 3 valence electrons. The valency that exists, like 3 valence electrons in the dopant external element like boron, if you consider, but it is surrounded by 4 carbon atoms. So one carbon and carbon boron bond is actually vacant. Okay, so that vacant vacancy that exists in the fourth bond constitutes the hole, and this hole accepts electron from the neighborhood. Trivalent impurities are called the acceptor impurities because each hole it contributes can accept one free electron during the recombination. The number of holes at any instant in the p-type semiconductor exceeds the number of electrons in the conductance band, right? So holes become the majority charge carriers and electrons are the minority charge carrier in the p-type semiconductor. So current flows through the material from the hole to hole along one direction. Then chloralkane react with the elements silicon at 300 degrees Celsius in presence of copper to give chlorsealants. This process is known as, the correct answer is actually Rauchow-Muller process. Okay, so Rauchow-Muller process. It is the most common technology for preparing organosilicon compounds on an industrial scale. This process involves copper catalyzed reactions of alkyl halides with elemental silicon, which takes place in a fluidized bed reactor. Although theoretically possible with any alkyl halide, but the best results yield in terms of selectivity and in terms of selectivity and yield occur with chloromethane Typical conditions are temperature like 300 degrees centigrade and pressure like 2 to 5 bar. These conditions allow 90 to 98% conversion of silicon and 30 to 90% of chloromethane. Approximately 1.5 metric ton of dimethyl dichlorosilane is produced annually using this Rocho-Moller process. So what is Rocho-Moller process? We can schematically visualize. So Rocho-Moller process. Rocho-Moller processes like this. Silicon attached on copper catalyst plus some alkyl halide like alkyl chloride is coming. The best result is on chloromethane. So that alkyl halide is coming, and then it will attach with this silicon bonded with copper bed. Cl, okay, followed by this kind of Cl. This silicon, this chlorine, it will go. So sorry, not this one, this will go. This is nothing. Plus copper catalyst will be there. By this process, several organosilicons we can make. For example, 2CH3Cl plus silicon leading to CH3 dimethyl silicon chloride. Okay. Then 3CH3Cl plus silicon can give to CH3 SiCl3 plus 2CH3 dot, which will combine to give C2H6, then 4CH3Cl plus 2 silicon can give to CH3 whole 3 SiCl plus CH3 SiCl3, or simply 2Cl2 plus silicon tetrachloride, then CH3Cl plus silicon plus HCl will give CH3HCl. These all are Rochomuller process of synthesizing organosilicones. Okay, so that's it. We have discussed some organosilicon process, some semiconductor materials, and our organosilicate, silicon dioxide, several types of silicates in alkaline earth materials. Okay, and some pigments also, berite, about the calcium carbide electrolysis, and silicon, some ores of silicon, right? So okay, that's all for today. We will meet in the next class. Thank you.